Alright, let's talk about what happens when you have a projectile that is not launched horizontally, but is rather launched at an angle. Right, so in these cases, you've got an initial velocity for these projectiles that exists both in the horizontal dimension and in the vertical dimension. So, just as a generic form, let's say you've got the ground here, and let's say you've got an object that's projected at some angle theta. It's projected with some velocity v naught, right, and it follows some trajectory. Now, if we're analyzing what's going on, right, halfway through the motion here, it reaches the peak height. Right, so what we can say is that the velocity at the peak in the vertical is 0 meters per second. Right, because again, we've got to keep our dimensions separate. You've got to examine vertically on its own, you got to examine horizontally on its own. Now, up here at the peak though, it still has horizontal velocity. Right, so at the peak, the vertical velocity is 0, just like if you took a ball and threw it straight up in the air, right, it slows down in the vertical, slows down until it stops at its maximum height, and then comes back down. Right, so vertically speaking, it's stationary, but it still has that constant horizontal velocity. Now, it's going to take some time to get to the peak. Now, the nice thing about a simple projectile problem like this, where it's launched, on level ground, is that if you know the time it takes to the peak, you know the total time is going to be twice that peak time. Now, other than recognizing that, there's not much difference between dealing with an angled launch versus a horizontally launched projectile. The biggest thing you've got to do is recognize that this initial velocity needs to be broken down into its component pieces. Right? So if we draw that bigger, we've got an initial velocity, right, fired at some angle, and some of that velocity exists in the horizontal, and some of that velocity exists in the vertical. And the amount of that velocity that exists in each dimension is going to depend entirely upon the angle of launch. Right? The closer that angle is to 0 degrees, the more of this initial velocity exists in the horizontal. The closer this is to 90 degrees, the more of this initial velocity exists in the vertical. So let's put some numbers on this and work out an example together. So let's say that we've got a ball player that hits the ball at an angle of 53 degrees. If the ball's initial velocity is 35 meters per second, we want to find the maximum height it can reach, the horizontal displacement, and the total time required for this motion. Alright, so we've got a ball that is launched at an angle of 53 degrees. And it has an initial velocity of 35 meters per second. And it follows a parabolic trajectory. Again, we know that the vertical velocity at the peak is 0. And we want to know the range, x. We want to know the maximum height, this y, and we want to know the total time. So, our first step here would be we need to find out how much of that velocity, this initial velocity, exists in the horizontal, how much exists in the vertical. So, let's break down our vector. We've got 35 meters per second at an angle of 53 got V naught x, we got V naught y. Now in order to get your individual components, right, you've got to use your trig functions. So this is your hypotenuse here. We've got our adjacent side, we've got our opposite side. So to find V naught y, we need to use a sine function. Right, where if we rearrange this, you get V naught y equals V naught times the sine of your angle. So V naught y would be 35 meters per second times the sine of 53. Again, make sure that your calculators are in degree mode and not radian, especially if you're in pre-cal. So 35 times the sine of 53 gives us 27.9, so we'll just say 28. So V naught y is 28 meters per second. Alright, now in order to find V naught x, we got to use our cosine function. Right, where the cosine of theta equals adjacent over hypotenuse. Again, if we rearrange that, V naught x equals V naught times the cosine of theta. So V naught x equals 35 meters per second times the cosine of 53. So V naught x comes out to 35 times cosine 53, 21 meters per second. Alright, so basically what this is saying is 21 meters per second worth of this initial velocity is in the horizontal, and 28 meters per second worth of this initial velocity exists in the vertical. Now keep in mind, horizontally speaking, there is no force acting, right? So there is no acceleration in the horizontal. So it travels at 21 meters per second horizontally no matter where you look, right? It's traveling 21 meters per second horizontally up here at the peak, while its vertical velocity is 0. Alright, easiest place to start. Let's start with finding the time it takes to get to the peak. Alright, so we can use our vertical dimension to find that time, where we're setting our final velocity, this Vy, as the peak. Right, so the time we'd be solving here is our peak time. So 0 is equal to 28 meters per second plus negative 9.8 meters per second squared times your peak time. All right, remember, your acceleration due to gravity is always a downward vector. It's got to have a negative here. Your initial your initial vertical velocity is an upward one, so it's positive. So let's go ahead and solve that out. So 28 divided by 9.8 gives us a peak time of 2.86. Make sure you're working this along with me. Sometimes I do make algebra errors, so you can call me out on it. So 2.86, which means that we know that the total time here is twice that. So 5.7. Alright, so we found one of our answers. Alright, now we can solve for either y or x. Either one doesn't matter. But what does matter is that you're being careful about which time you're using. So let's say we want to solve first for the range, that horizontal distance. We can rearrange this to our x equals vx times time. Well, if we want the range, the time that we need to be plugging in is your total time. Now, if you plugged in your peak time, you would be only finding how far it went horizontally to the halfway point. So, x is equal to that 21 meters per second constant speed times 5.7 seconds. So our range there, so 5.7 times 21, is 120 meters. Now let's find our maximum height. So we could use either one of two equations, but this one's probably easier. V final y squared equals initial y squared plus 2g times your
Please release your freshman and KCAL students.
vertical displacement.
Please release your freshman and KCAL students.
Alright, so again, we're treating this as our peak. So this would be 0 is equal to 28 meters per second squared plus 2 times negative 9.8 meters per second squared times our displacement. So if we solve that out, we get 28 squared, 6. A vertical displacement of 40 meters. Now, one thing to be careful with. You can also use this equation. Now, if you do use this equation, the time you need to plug in is that peak time. That will give you your maximum height. If instead you plug in the total time, your vertical height, that y, is actually going to come out to 0, right? Because its height right here is 0, right? So you want to be careful with which times you are plugging in to each one. So I'm going to be posting up a set of practice with this, see what you can do with it. And again, come to the live sessions and we can talk about all of this. See you soon.